In certain high-density star clusters, an invisible central mass warps the light from background nebulas into strange, arcing distortions. This distortion marks a region where matter is packed so tightly that its gravitational pull captures everything, including light. These objects first appeared as mathematical anomalies. In 1915, they were predicted as exact solutions to the equations of general relativity, pointing to a puncture in the geometry of spacetime. The boundary of this puncture is the event horizon, a physical point of no return that defines the black hole's outer edge. Black holes function as the universe's ultimate gravitational engines. They're the specific regions where our baseline understanding of physical reality ends. Most of these engines begin with the death of a massive star. When a core at least 8 times the mass of the Sun runs out of fuel, it collapses and explodes as a supernova. In the early universe, black holes also formed through the direct collapse of metal-free gas clouds, bypassing the stellar phase entirely to reach masses up to 1,000,000 times that of our Sun. We can now detect these objects as they grow through massive binary collisions, which release bursts of energy in the form of ripples through spacetime. Active black holes possess a distinct anatomy, including an ergosphere and a superheated accretion disk. Just outside the horizon is the photon sphere, where gravity traps light in a continuous orbit. Finally, all mass concentrates at the singularity, a single point of infinite density. Mapping this anatomical structure transforms black holes from theoretical concepts into physically measurable cosmic objects. Astronomers classify these objects based on their mass, which ranges from city-sized remnants to galaxy-anchoring giants. Stellar mass black holes are city-sized and found throughout the galaxy. Supermassive black holes, by contrast, are millions or billions of times the mass of our Sun and reside at the heart of nearly every galaxy. Transitioning from theory to observation required a planet-scale radio telescope array to capture the specific way these objects interact with light. In 2019, the Event Horizon Telescope collaboration released this image of the black hole at the center of galaxy M87. It is the first direct visual evidence of a supermassive black hole and its shadow. Seeing this shadow shifted black holes out of the realm of theoretical physics and into observable, empirical astrophysics. As an object plunges towards an event horizon, the gravitational pull at its leading edge becomes significantly stronger than at its trailing edge. These extreme tidal forces result in spaghettification, a process that vertically stretches and horizontally compresses any object until it is destroyed. Directly at the event horizon boundary, the physics shifts to subatomic quantum mechanics. Virtual particle pairs constantly appear near the horizon. When one particle is captured by gravity and the other escapes, the black hole emits energy known as Hawking radiation. Because of this quantum leakage, black holes will slowly evaporate over extremely long timescales. Specific legendary black holes provide the data needed to test our models of cosmic evolution. At the center of the Milky Way sits Sagittarius A star, a 4 million solar mass anchor located approximately 26,000 light-years from Earth. Recent observations of the Infinity Galaxy have revealed supermassive black holes that formed far earlier than current theories predicted. Data from orbital observatories like Hubble and Webb are challenging our understanding of the timeline of the early universe. Discovering these ancient titans forces astrophysicists to rewrite the evolutionary history of the first galaxies. Modern science currently stops at the singularity, where our mathematical models of the universe fail to describe physical reality. This creates the information paradox, the unresolved debate over whether quantum data swallowed by a black hole is permanently lost or somehow preserved. Research suggests that surrounding dark matter halos may also be secretly influencing the rotation, ergosphere, and shadow of these objects. Pulling back from the singularity reveals exactly how these extreme objects anchor the largest scales of the cosmos. Black holes remain the essential testing ground for physical unification, the only known environment where the rules of gravity and quantum mechanics are forced to interact.